All right, can you guys see this okay?
Yep.
Okay. Let's see here. All right, cool. Okay. So basically what we'll go through here, we'll just go down this file that I have typed up. That's just the practice. Um, so the first thing we'll kind of cover, like the first topic, is going to be classes. That's kind of what we did at the beginning of this of the class, like all the way in the beginning. So this class that you see, you've seen a bunch of times, but we'll go over the different definitions and vocabulary. One of the biggest things on the exam and even in the quizzes is going to be understanding the vocabulary that goes around everything you guys learn. Um, while there are some specific questions that are going to be like, what is the definition of blah, blah, blah? More often than not, where the vocabulary comes into play is just understanding what these terms and words mean for the questions themselves. So there could be a question that's asking something that uses, three words that you don't really know what they even mean. And that's going to be really hard for you to understand what the question is asking to begin with. Um, so I think it's really important to understand all of the little technical things and all of the definitions we give that surround C++ and programming so that you can clearly understand what the question is even asking to begin with, right? So we'll go ahead and go over some of those definitions. I think a lot of them come from the classes themselves. There's other definitions here and there, but I think a lot of them stem from classes, especially in C++, the difference from what you guys did in Java. There's a little bit more terms or different terms than you guys are used to. So my original question, or my initial question rather, for classes is what are the big three that you should make anytime you're doing dynamic memory?
Um, Copy constructor, copy assignment constructor,
And
and
then
a
I think
destructor.
if someone's answering, I might not be able to hear you guys. Give me 1 second. Um, okay, I might be able to hear you guys now. Okay, I see some stuff in the chat, so let me just go ahead and share this again. My Zoom's been acting up recently. All right, cool. So it looks like all these answers are correct from what I can see. So copy constructor, copy assignment operator, and the destructor. So those are the big three we need. So it's going to be copy constructor, copy assignment operator, and destructor. So these are the big three that we're going to need anytime we're dealing with dynamic memory. The reason is if you need one of these, more often than not, you're going to need all three. And that's because if we're dealing with dynamic memory, we need to destroy that dynamic memory so don't get memory leaks. So that's the destructor. And then if we're dealing with dynamic memory, we need to define a copy constructor and copy assignment operator so that dynamic memory can be properly dealt with during those copy operations. What the compiler implicitly is going to give us for that dynamic memory is not going to be sufficient for what we want from the program. It's going to do a shallow copy and it's not going to work. So we need to define those copy constructors and copy assignment operators to give us some type of deep copy that'll give us the functionality that we desire. And I will go ahead and go over a few of those later down, but the first things first was the definition. So I'm sure you guys can see the second question. What are the class members defaulted to, public or private? So if you're going to go ahead and type up a class, what is the default going to be? Let me scroll down here. Private. Yep. So this is going to be private. And then for struct, what will it be? Public. Yep. Sweet. So it'll be public for struct. So those are the key things you need to remember. That'll come up if we are typing up a class. Anything that's typed up that isn't underneath a private or public tab is going to be private. On the other hand, if you have a struct, anything that's typed up in a struct is going to be public. So if we had struct my struct and a definition for this, like int my variable, this is going to default to public, right? So this will be public and we need to actually make it private if we want that functionality. Differences between structs and classes, that's pretty much it, other than what is typically done. I think I kind of went over this a little bit with the linked list, but structs are more typically used as a data container that doesn't need a lot of functionality, meaning we're not really making functions for it. Where a class is something that we want to represent like a real life object that will have some type of functionality. So getters, setters, mutators, all of that good stuff. Um, that isn't to say that you can't have functions for structs. You totally can. I think it's just a little bit less common. Most of the times when you start building functionality, most people end up defaulting to a class. But what you guys see out there might differ. This is just coming from kind of my personal experience. But if it's ever a question, the only difference between structs and classes are going to be that default to public or private. So cool. So we can kind of keep going down here. Like I said, feel free to interrupt me with any questions you guys have. Um, so uh, with the classes themselves, this is what would be considered a class declaration. So we're not actually giving the definition of a class. We're just declaring what that class is. You don't really see what's on 23 and 24 a lot most of the time because if you're just going to write what the class is, you're going to pretty much define it right there. But just in case definitionally a question comes up about whether it's a declaration or a definition, that's considered a class declaration. It's pretty much the same concept as all of these functions being declarations. A declaration is anything that you're just writing, but not actually defining what it is. It doesn't have a definition associated with it. Line 27, and then all the way down where the open brackets are for this class, this is all considered the class definition. So this entire whatever's inside the open brackets after the class is going to be the definition. This is what we're defining the class to be. Okay. I think some students get confused and assume that's the class declaration, and then the definition is when we do the functions. But that is more dependent on the functions themselves. This is specifically talking about the class. The function definitions are typically done in the source file, but that is for the functions themselves. So we kind of keep going. Yeah, go ahead.
Sorry,
Yeah.
yeah. You would say that the when you're like, for example, when you're doing the definitions for the class function, you'd say the class member functions, right? You're defining the class members, right? Is that how you'd say it?
Yeah. So are you talking about like any of the functions, like the class member functions are defined in the source file? Yep.
Yeah. So then you have you have the inside of the class definition, you have the class member declarations, and then in the source file, you have the class member definitions, right?
Or the class member function definitions. Yeah, that's right.
And then if you're using headers, you have to put it on. I mean, sorry, if you're using templates, you have to put it on one header file, right?
Right. Yep. That's all correct.
Okay. Thank you.
Yep. Yep. And then just going over like legality versus should, I will say that just for the purposes of this, I do have all of the function definitions actually typed up in the same like file, and you can actually see this isn't even a header file, and it will still compile and run okay. But when Fox is asking questions of what you should do, everything you said is correct. You should be putting templates all in the same header file. If it's not a template, you should have the class definition in the header and the class member function definitions in the source. So there's, and it sucks, but there's differences between like what's actually allowed, like what the compiler will allow, and then what you should do to stay as organized as possible. And most of the time when Fox asks those questions, he's talking about the latter, where he's talking about how to stay as organized as possible and what you're going to mainly see like out in industry and what is the like status quo, if that makes sense. So cool.
Thank you.
Yeah, no problem. Okay, so yeah, going down along this, these are just basically class member, just class members, right? These are the different data types that we have that's within this class. We can see that this one's going to default to private. And then this is going to not default to private, but these are defined as private. And then these are public, so that they're going to be accessible without any getters or setters. We can just have access to these things. Private data is what we consider like protected. We're not going to let the user manipulate it. Public is what we're going to allow the user to manipulate all they want. We want them to have access to it. We're opening up our encapsulation for them to use it. Yeah, Franco, what's up?
It's probably better if I ask this later, but just right
Yeah.
now, if you could, like at some point just go over something that's always confusing for me, like when are like the syntactical difference of when you're passing in a reference or a memory location of a pointer. You know what I mean? Because
Yeah, I got you. Yeah.
with the ampersand, sometimes I'm like, I don't know if this is a reference to to data or if it's like the memory address, or is that the same thing theoretically? I don't
Um,
know.
yeah, we will. I'll default that for later on. We'll definitely be going over all of that. So good question. And we'll answer that later on. Yeah, yeah. And I'll make sure that to make sure I'm answering the question that you had.
Thank you.
Yeah,
Sorry
no
for that.
problem. Cool. So yeah, that's just basically the public and private. And one thing I want to make clear is you can have like multiple of these. Like I could define another private section and put in like another variable here, and then I could immediately do another public. So there's no limit. You aren't limited to just doing private and public and then trying to fit everything in there. You can continuously do this. It's not very common, but you can if you want to. So okay, so going on with this, we have a bunch of declarations. These are all function declarations. So splitting up into two different parts, there's accessors and then there's mutators. So the accessors are going to be your getters and your mutators are going to be setters, right? So we're actually mutating some kind of object. And then the getters are just accessing some type of data from the object itself, right? We could also have what's considered behaviors, and behaviors would be I can't think of a good one for a student class right now. Maybe I guess you could do like adding a class would be one. I won't write the definition of it, but like add class where it takes in like a string name of a class, not to be confused with a class in C++, but just a class they'll take. And actually, looking at that, it won't let me name it class because that's a keyword. So it could be name of class. And this would be considered like kind of a behavior where it's going to manipulate something about the system, but do something with it. I think probably, honestly, a better one would be like print all classes. I like that better. Print all classes. Basically, anything that's not a getter or a setter is most likely going to be some kind of behavior, right? Arguably, I guess you could consider print all classes being a getter because you're just, printing stuff out. But if we're going to compare it to like the linked list, a behavior would be something like add node head or add node's tail, something like that. Something where you're actually changing the behavior or making the object do something as opposed to just setting or getting something. So those are your three different types of functions. It's going to be accessors, mutators, or some type of behavior. And sorry, I couldn't come up with a streamlining example here, but you can just think to yourself, am I getting or setting data? No, it's going to be a behavior. Unless I guess it's a constructor, which hopefully you guys understand the difference of those, which we'll go over in a second. With these getters, I put a const at the end of them to basically protect the this keyword. So let's take a second and talk about this const keyword. So anytime you see const at the end of a function, end of a function declaration or definition, basically what this const is referring to is actually making the this keyword a constant, meaning we're going to protect this. We're going to actually protect this function to not manipulate anything about our object. So the object that's actually calling this function won't be able to be manipulated in any way. And I think the hardest thing for students struggling with this const keyword is that it's kind of hard to conceptualize that we're kind of protecting ourselves from ourselves. So we're protecting our code from ourselves, meaning if we're the developer for this code, and if I'm doing a get age function, if we kind of take a look at the definition of this get age function, basically right here, all we're doing is returning an age, right? So at no point in the functionality of this getter should I be doing something like setting the name to something, right? Where I can set the name to Matt or something, right? This basically won't allow this to happen because, well, a couple things. Matches these opera string. Okay, I guess name is that should be a string. What I was hoping, let's just do age. Try to change the age. Clearly, I messed something up there. 10. There we go. So basically here I'm trying to change the age to 10. And what it's yelling at me about is that it must be a modifiable L value, like left value. Uh, and basically that's what this const is preventing. It's preventing me from changing anything about the instantiating object. And this is important because we're just trying to get data here. We don't want to manipulate anything. So that's what I mean when I'm saying it's protecting us against ourselves, especially if you're working on a team as well. Let's say you wrote this get age function and then a team member wanted to change something about your code. And for whatever reason, they put in like something to change in this get age. And then the compiler yells at them and they're like, hey, man, this is a const function. And they're like, this is a read-only function. Maybe it was defined that way on purpose. Let me take a step back and reevaluate what I'm doing here. So that's kind of the purpose of that const. And I think it's just confusing because most of the time when we think of const, we think of it in terms of the user and like protecting our code against the user. But in reality, we're kind of self-guarding against ourselves. Yeah, Franco, what's the question?
So basically, like theoretically, all getters should have a const at the end of their definitions, right? Because we shouldn't be changing anything in this.
Yeah, that is probably a really good rule of thumb, I'd say. There might be some weird edge cases where your getter for some reason does need to change something, but I would say 99% of the time, your getters should just be returning something, meaning they should probably be a const. I forget the name of the principle within programming, but it's the idea that functions should only do like one thing. So if you think about it, that if it's just to get the age and you're trying to do something else, maybe that should be left to another function. So, but yeah, I would say you're right on that.
I have a question.
Yeah.
One of the things I don't understand is because I understand that in order to call certain things, you have to do this dot, or sometimes it's this and the arrow. I don't know when you'd use either, because I mean, that was something I had trouble with in the linked list project, but I managed to get that down.
Yeah, for sure. So I would say, if I'm thinking about this correctly, that the only time you truly do need this keyword is something like this constructor here, where basically what you're passing in has the same name as your class member variable. So for instance, if I took this keyword off of line 95, we now have age equals age. And hopefully this already looks kind of wrong. This looks weird to us, right? To have age equals age. And what's actually going to happen is what's being passed into this constructor, like age right here, it's going to get set to itself. Meaning what we passed in is going to get set to what we passed in, meaning it's never going to actually change the age of our class we're trying to instantiate, of our object we're trying to instantiate. So we basically tell the difference by putting a this on there. And again, this is, and I'll kind of print this out a little bit later to make it even more clear, but this is just a pointer to our calling object. So what I'll print out later is just that these addresses are going to be the same. So hopefully that proves that it's the exact object in memory. And that's why we need this arrow operator, right? Because it's a pointer. And it basically makes it, as the programmer, more explicit that when we're referring to literally this in our code, we're referring to the calling object. But that's pretty much the only time you need it. When you ask, like, when do I need it? That's pretty much the only time. Or you could do something like this, where you don't take in like the same exact string as what you named your class member variable. I just put like an underscore in front of here, which is pretty common to do. So you don't have to do something that looks like this. And then you can see ID number here, which is a pointer because I wanted to be dynamic. I just set it to a new int. I didn't have to use this keyword either. And then same goes for any, this is outside setters or getters and other functions. If it belongs to your class itself, you don't necessarily need to add like this keyword. So that was kind of long-winded, but did that answer your question?
Yeah,
okay.
It did.
Cool. Yeah, good questions, guys. Definitely keep them up. Okay, so that's pretty much, I think, everything on these functions. I think I went over the const, so that's good. So we can kind of go over the default constructor and the constructor. So your default constructor and your constructor are going to not be a part of the big three, right? So definitely not a part of the big three, because usually we're going to want these for every program we write, regardless of if we're using dynamic memory or not. You don't have to have them. It will do a implicit default constructor. But if you want it to do something, meaning your program, you want your program to do something different than what it's implicitly doing, you're going to have to write your own, right? Something to keep in mind is you can only have one default constructor. Hopefully this makes sense, because if you have two or more default constructors, it's supposed to be a default, meaning the program's not going to know which one to choose, right? So this is kind of a way you could write your default constructor, where you just take in all the arguments within the actual line, and it will default them to what they have set equal here. Your other option is going to be something like this, which I'm sure you guys have seen, where it doesn't take in any parameters, and you can do like this name equals, this name equals in, and then a. And then similarly for age and year, you could do those two on the next lines. And then this is an example where we don't really need this keyword either, because we don't have anything named name. So this is just going to know, like, even if I click on this, it actually brings me up to where I have the name defined. So hopefully that ties into when we needed this keyword or not, that it understands what this is. So these are your two options for your default. I'm pretty sure you can only have like one of these, because like I said, it's not going to know which one to call really. So we can just keep this one for now. For your regular constructor, I kind of have these out of order. Your regular constructor I've actually defined outside of the class. Just that's the way I ended up hacking this up. You guys, if you've been coming to my labs, and I think a lot of you have, you've probably seen this class about 100 times, but I think it's helpful to work with something you've seen before, just so the concepts make sense. But this is just our defined constructor, where we are going to take in some parameters, and then we're just going to set those parameters. And the only other thing we need to do here is just set the ID number to a new integer. They definitely could set this. They could definitely pass in like, and I won't keep this because I don't have it defined everywhere else in my program, but they could take in like an integer here that's called ID number, and it doesn't even have to be a pointer. Then you would basically just dereference ID number and set that to the ID number that they passed in. And you might have to use this because it thinks that it's trying to dereference this, meaning the ID number here. It gets a little bit confusing. Let me just do that. So you could do something like this, where they don't necessarily have to point in a pointer, and probably shouldn't, because we want to actually keep track of it, meaning we're going to make the new dynamic memory ourselves, and then just dereference that dynamic memory that we set up and set that equal to what they passed in. So hopefully that makes sense. This is yelling at me because I don't have it defined up above. And then we won't keep that because, like I said, I don't have it defined anywhere else. But that's pretty much what your constructor is going to look like. It constructs your object, right? And you guys have seen this a lot and done this a lot already. Okay, so for the big three, so here we have our destructor. This one's pretty simple. I only have one thing that I'm dynamically allocating, meaning I only have to delete one thing. For those of you that did the linked list project, and hopefully all of you did, but you recall from that you actually had to manually loop through and delete every single node in the list, right? Because that's how many new calls you made. So your destructor is going to be in charge of basically any memory that's left over in your system. You're going to have to delete it, okay? And then for the copy constructor, this is going to be called when your object, like if you're trying to instantiate a new object using another object, it's basically going to copy that other object and create your new object out of that. So in this situation, we only have one existing object. And because we only have one existing object, that means we don't have to delete any other memory from your like original object, because there isn't one yet, right? So we're going to go ahead and do a shallow copy for all the stack variables, which is perfectly fine in this situation because they aren't pointers. So a shallow copy is fine. For those of you guys, again, who did the linked list project, depending on how you did your copy constructor, you probably saw that you couldn't just copy your node count over. Depending on how you did it. And that's mainly because probably the next thing you did was something with either the add tail or actually incrementing your node count manually. So that one was kind of a specific case where you couldn't just copy over stuff shallowly, even though it wasn't a pointer. But definitely for the like head and tail, you couldn't just copy those over in a shallow way, right? Because otherwise your head and tail of your new list would be pointing to the head and tail of your old list, which is not what we want. So that's why this shallow copy is okay, because they're not pointers. For the deep copy, and this is what we need to do, this is why we're defining this copy constructor, is because we need to make a new integer for this ID number, and we actually need to dereference the ID number and the other ID number to copy that over. So we're making a new one on the heap, and then we're just copying the value into that new memory on the heap. For the copy assignment operator, we're overloading this equal symbol, and it's going to be the same thing as a copy constructor, where we're going to do a shallow copy for the stack variables. And then we're going to make a new ID number and dereference. This line is the same as this. I just did some different syntactically, but it's going to be the same thing. The only difference here, though, is we need to delete the old ID number, because in this situation, you have object A being copied into object B, and both of those objects already exist. So if you just copied over everything from A into B, and we didn't delete the old ID number, that ID number would be leaked memory. So we need to make sure that we take care of that. Again, if you compare it to the linked list project, you probably had to go in and delete all of your old list before actually making a new list within the copy assignment operator. Yeah. And then you need to return the this keyword, which is different than the copy constructor. The copy constructor, it's a constructor. It doesn't return anything. The copy assignment operator can return whatever it wants. It could be void. It could do whatever. In this situation, we definitely want it to return a reference to the new object that, or to the object that we're copying into. So, yes, Franco, question.
Real quick.
Yeah.
I always understands, but then I forget it again. Real quick, how can you delete it and then delete the ID number, right? Which is like the old ID number when you have delete ID number, right?
Yeah.
And then access the data afterwards. How does that work again? Yeah, then you have old student.id number.
Right. So when we're deleting this ID number, we're actually deleting this ID number. We're not actually deleting the ID number of the old student. And the more I do this, the more I realize I think I probably should have called this like the right hand side, to be honest. I think calling it old student is actually a little bit confusing. It made sense in my head, but the more students question what I've done, I think it's a little not clear. So the ID number, what I'm truly deleting is the this ID number. The right hand side, like again, this assignment would be like if we had and of course I can't type this here, but if we had student like Trevor being defined, and I'll show this later on, and then student Brad being defined, and then we did Trevor equals Brad. Brad right here is the right hand side, so we're leaving his alone. We're not going to delete his, but we're going to delete this, which is Trevor. So this is referring to the left hand side of this operator. So we need to delete Trevor's ID number because we're going to immediately replace that with whatever Brad's ID number was.
Okay.
Yeah.
Thank you.
So yeah, no problem. It's definitely a little bit confusing, and I think the more you work with these things, the more they end up making sense. But some of these things can be pretty confusing. Cool. Okay, so we went over all of this stuff. This set age, it looks a little different than just kind of a normal setter, just because I wanted to show that sometimes you want to actually like check stuff in your setters. Just some like edge conditions. You did this a lot in the linked list where you basically like if they gave you an index that was like out of bounds, right? You just return an error to them. Stuff like that is really common. So for the age, I could easily have like thrown an error if they, passed in a negative age, right? That shouldn't be possible. If anything, this age should be an unsigned int, but all right, cool. So that's pretty much it on classes that I have to go over. That was probably like the longest topic just because there's so many definitions and working parts. Any other questions about like classes in general? I have other stuff I'm definitely going over, but just about classes, any other questions? All right, cool. So let's go ahead and move on. We can do, let me do this. We'll go take a look at pointers real quick. All right, cool. So a couple questions that you guys probably just saw the answer to anyways, but first question, to use a pointer, do they need to point to memory on the heap?
By they, do you mean the pointers? Like, do the pointers need to point memory on the heap?
Yeah, so if we use a to use a pointer, do the pointers need to point to memory on the heap? So it's kind of confusing to ask, but basically, if I'm using a pointer, does it have to be used with heap memory?
No, that's only if you like allocate memory on the heap, right?
Right, exactly. So no, yeah, a couple of you guys answered that, which is the correct answer. The relationship, because this is a relationship I see confused a lot. If you are using a pointer, it doesn't have to use dynamic memory. But if you are using dynamic memory, you have to use a pointer. Okay, so that's kind of the relationship that you guys should remember in your head. Okay, so next question: where are the pointer variables stored? The answer choices here are like the stack and yeah, you guys got it. The stack or the heap, right? So these are going to be on the stack. And another question would be where are dynamic? I don't have this typed up, but where would dynamic memory variables be stored?
Heap.
So close, and that's yeah. So it's actually going to be on the stack. Usually heap is the answer people go with. And you would be right to think about the memory itself. But when I'm asking where the dynamic dynamic memory like variables are going to go, variables are always going to be stored on the stack. So if I did something like int my dynamic variable equals new int, my dynamic variable is going to be on the stack and it's going to point to memory that is going to be on the heap. So just make sure you're being really vigilant on the tests and other quizzes going forward, that if he's asking where variables are stored, it's always going to be on the stack, no matter if it has a new keyword or not. The new is only going to be about where the memory is stored. So if he asked you where the memory is, then the answer would be the heap. And I probably asked it in a confusing way because I think I asked like where is the dynamic memory variable. So it wasn't a great question, but hopefully what I just went over is clear. So next one, can int pointers point to a different data type? So can int pointers point to a string data type or a character data type? Okay, fair enough. I don't know. Yeah, so the answer to this one's actually going to be no. So we can't do like int pointer, what I have, like my variable equals character, or like new character. This should yell at us. It would probably yell at us more if I actually did this in a main, but we can't have something like that.
Is this because like when you're declaring the int pointer, you're declaring only the memory, enough memory for an int?
That is an excellent that's a good guess, like for sure. That's what most people think. Weirdly enough, all pointers ever are actually just going to be like 4 bytes, I believe. Why it won't let it though is because it is actually an int pointer. So it only knows how to point to things of a certain size. So the size is kind of there. But actually all pointers ever are just going to be 4 bytes. Which is interesting to know in and of itself. But yeah, it's mainly just like about data types and where it can point. But that was a good guess though, for sure. But yeah, the answer to that one is going to be no. Okay, so let's go over this right here. So this kind of uses my the class a little bit, and this needs to be, whoops. This right here needs to be capitalized. Okay. So my question to you guys is what the output of 190 is going to be. So don't worry about 187, but what is the output of 190 going to be? And then get age, I kind of briefly showed it, but that's just going to return the age. Yeah. So 22. Let's go make sure I'm not a liar. Okay, compiled. That's surprising. Okay, cool. I'll go over this in a second, but 22. So that's going to be what's printed. So you were right. What's going on here is we're setting Trevor to student. So this is just the default constructor for Trevor. And then we're basically, we have a student pointer that's going to point to Trevor. And what we can actually do here is manipulate Trevor through that pointer. So really the purpose of this is just demonstrate that we can change things indirectly using pointers. And that's even allowed with like class objects themselves. We're not just limited to like int pointers or character pointers. We can actually make pointers to our classes or objects themselves. So when we do pointer set age, pointer is pointing at Trevor. So that would be the same as doing like Trevor dot set age. 22. And that's why we get 22 here. This 0 originally was printed out because of the default constructor. So that's why this one is 0. And then as far as address of this, let's actually take a step back. I'm sorry I didn't do this earlier, but let's go ahead and print out the address of Trevor. So if we got the address of Trevor, or I could print out the pointer, but let's do it this way. So this address of this, if we go check out where that's printing, that's actually printing in the set. So I'm printing out the address of this. And what I'm trying to prove to you guys here is that this keyword is going to be the same as Trevor. So if you take a look at these addresses right here, they're the same, right? And that's because the this keyword is literally like the Trevor object. It's the exact same object in memory. And that's what we mean when we say that this is the instantiating or the instantiating object, the calling object of that function. So any questions about that?
Yeah, so basically instead of directly accessing the class member function, right? We're going through the class, like going through the class and then accessing this public class member. You're just using the class pointer and then just pointing to the class member function directly without having to go like through the class kind of, right?
Yeah, you're talking about with Pointer and Trevor. Is that what you're talking about? Yeah, basically. Truly looking at this, again, a lot of what I'm doing today is super trivial. It's more about like explaining the concepts behind it. Obviously, if this was the entire code, making a pointer here would be like totally that'd be way too much effort, right? But you are right that yes, we can indirectly access it through pointer, basically. Yep. Cool. So we can get rid of this, and then we can move on to the next one. So don't need that one. Okay, so this is just some basic pointer stuff. I'll manipulate a few stuff here and there just so we can get comfortable with it. This is just what I had at the end of last class. So my question here would be, what is going to be the output of this line right here of 226? And I don't remember either, so I'm going to take a look at it as well. And then you can shout out the answer, type it in when you guys get it. So 7, that's going to be close. Yeah, close. So take a look at what's happening on 223. 10. Yeah. So let's go ahead again, make sure I'm not lying to you guys before I explain it. All right, so we get 10 here. So let's kind of step through this. So x is being set to 7. Y is going to be set equal to x. So now both x and y are 7. And then we have two pointers. We have pointer and then pointer 2. Pointer is set to x and pointer 2 is set to y, the addresses, that is. And then on 222, we set pointer 2 equal to pointer, which means now both pointer and pointer 2 are going to be pointing to x, meaning they're like kind of referencing x, right? And then so if we change x on 223 to 10, that means when we dereference what's pointing to it, it's going to change to 10 as well. So yeah. Cool. So let me go ahead and just play around with this a second. And if we did something like this, what would the output be? Not quite. Well, actually, yes, because this is going to be actually, yeah, I think it might be 8. Yeah, okay, cool. So I was confusing myself there for sure. So it's the same process that we had before, except now we're going to change x to be equal to 8. And then we just set pointer to x, which we had just changed to 8. So definitely this one looks a little bit confusing because it's weird to see x being set to 10 and then this being set to x and then saying this is now going to print 8. But remember, this line right here is indirectly changing what x is. A lot of times with questions like this, it's probably helpful to actually write them out and like mark down as each thing changes what it's being changed to. With stuff like this, you got to be really vigilant because a star in one place or a swapping of lines can make all the difference. So, and I'm sure you guys had that painful experience in the linked list project. Yeah, so if we did something like this, then I think this is really obvious, but this would just be 10. So again, this stuff is super trivial, and the pointer questions you're going to get on the exam are probably going to be a little bit more complicated. But if you understand the basic principles of those, you should be able to work your way through those questions. You know, with programming, there's infinite possibilities of what can be thrown at you. So really understanding the basics is going to help you problem solve your way through the rest of the problems. It's just like probably a lot of you are in like calc and physics. Like if you understand those base principles, then you just need to apply those to the other questions you got. So, okay, cool. Any other questions about pointers in this situation right here? Franco will still go over the passing by reference and stuff later on, but just basic how like pointers and references kind of operate.
Perfect, thanks.
Cool. Okay, so let's go ahead and comment that out. So we'll go over some dynamic memory stuff, mainly about memory leaks, because that's pretty important. So my question to you guys is going to be, how many bytes are going to be leaked here? And assuming each int in the array is 4 bytes. And what I mean by this is like if this is 10 integers, each one is going to be 4 bytes, meaning this new call right here is actually 40 bytes in and of itself. So looks like I got a question. So the pointer, let me scroll back up. Sorry about that. So the pointer has a memory of address X and pointer 2 is set to the same memory address. So if you change pointer 2, you change X. That's exactly correct. Yeah. And it's the concept where we can basically, if we're pointing to something, we can indirectly change what we are pointing to. That's kind of the whole benefit we get out of pointers, is to be able to manipulate things using the pointer. With the linked list, that's how we made the entire linked list functionality, right? If you had like head next is equal to something, we're changing that next node via a pointer. That's how we're actually getting to the next node.
So basically in C++, you can choose whether to do pass by reference or pass by value just by using pointers or not, right?
Yeah, that's 100% correct. Yep. Okay, so do we need to memorize the size for different data types? No, and the reason is because the data types in C++ are actually dependent on the machine. So if he gives you a question that asks something about like how many bytes are leaks, he will have to tell you how big it is on the machine that's being asked. Like if you had a 8-bit, like this is a 64-bit machine. If you had like an 8-bit machine, I don't know the exact conversion, but it's possible an integer could be like 1 byte, right? Because that's like as big as it could be. So that's why they do have to tell you. So there's no standard in C++ on how big a integer is or how big a character is or anything like that. So Java is a little bit different, but no. Cool. So, all right. Yeah, my question to you guys is how many bytes are leaked here? You can see there's 3 news and there's 3 deletes, but I will give you a hint. I'm not tricking you here. The answer isn't going to be 0. So kind of work your way through that one, and then let me guys know what you think this like how many bytes are going to be leaked here. Yeah, both of you are right. 44. Yep. So, yeah, so not 16, but that's okay. So let's kind of walk through this and figure it out. So, I think we can agree that we are initializing like 64 bytes here, right? These are all going to be new. So 40, 20, and 4. Where we're going to start leaking memory is in these 2 lines right here. So when we set pointer equal to pointer 2, what's happening is pointer was originally pointing to 40 bytes somewhere, right? When we set pointer to pointer 2, we're actually moving where that pointer is pointing to. And we're basically, I like to think of it as like we're abandoning that memory that we were initially pointing to. And now there is like no way to get back to those 40 bytes. So if I go ahead and kind of draw this out here, if I had like the 40 bytes right here, and then 20 here, and then 4 here, and pointer is pointing here, and then this is pointer 2 pointing there, and pointer 3 pointing there. Hopefully this makes sense. As soon as I do line 238, where I okay, sorry. Yeah, where I basically point pointer 2, that breaks this connection, and we are now pointing pointer 2, pointer 3, or excuse me, pointer 2. And then now we're going to do the same thing when we do pointer 3 is equal to pointer 2. We are going to break this connection, or abandon the memory we just made and point it here. So that's why it's key to understand what setting pointers equal to each other actually does. And now what we end up here with, hopefully this is clear, we've leaked 40 plus 4, so 44 bytes. Let me go ahead and prove that to you. I'll go ahead and compile this, and it doesn't, because I have 2 mains. So I don't know if that's a question, but C++ can only have 1 main, and that's hopefully clear right there, that it's going to yell at you for having more than 1 main function, that is. So let's try to compile that again. We can run this through Valgrind, which I think I've shown most of you before. So we can check the leak, like how much we've leaked. So we can see that's 44 in 2 blocks. So 44 bytes is what we've basically leaked here from the heap, right? So all of these deletes, you can say, well, like, wait a minute, we're like deleting, we have 3 deletes, like the deletes are matching up. We should have like a net 0. It shouldn't leak anything. If we go ahead and run this normally, what you're going to see is that it actually yells at you and crashes the program about having a double free. And this is because everything is pointing at this location. So when we call delete to pointer, that's perfectly fine. It's going to delete this memory. But then when we call delete to pointer 3, it's trying to delete memory we've already deleted, and C++ is going to crash and burn when that happens. And then same thing with pointer 2. And actually, it won't even get to deleting pointer 2 because we've already crashed and burned when we try to delete pointer 3, right? So let's assume we're not writing like a super trivial program here. Let's go ahead and try to like fix this per se. So you have a couple options, I guess, depending on what your program's trying to do. If you're like actually trying to point all 3 of these for whatever reason at one location, you can go ahead and just make another pointer, right, that you can have that's going to preserve that information. So not to get confusing with all the numbers, but we can set a pointer 4 to be equal to pointer, and we can do int pointer 5 and set that equal to pointer 2. So now what we'll actually have, and then we can delete these instead. So now what we'll have is before we abandon these things, we'll have a pointer. What is it? Pointer 4 that's going to point here, and a pointer 5 that's going to point here. So now we have we have accounted for all of our memory, and we're able to reference these things to actually delete them. Remember, our memory leaks are going to basically stem from issues where we no longer can reference our memory in any way, meaning we don't have a variable name to actually access those things. So if we go ahead and run this, this will give us the behavior we expect, meaning we don't have any memory leaks here, except I have 4, so I did something dumb. Let's see here. So pointer 4 equals, so this is where I'm looking, where I have 4 bytes. Pointer, I wanted to delete pointer 2. That's what it was. Okay, so let's go over actually what happened there. A little learning experience. So I deleted pointer 4 and 5 perfectly fine. So 4 and 5, which was actually pointing to pointer 2. So I meant to point this to pointer 3 is actually what I meant to do. And then I need this to delete pointer 2. So I know this is getting kind of weirdly confusing. It wasn't supposed to be like this. But this will give us 0? Yeah, 0 memory leaks. Basically, all this has to do with just keeping track of your pointers and where they're pointing to. Again, incredibly trivial. If you ever find yourself having 3 pointers to one location, maybe rethink what you're doing. So the other way to fix this would be to make the assumption that we no longer need the things that were like, if we're setting pointer equal to pointer 2, maybe the assumption is we no longer need pointer. So we should just go ahead and delete that memory. And same goes for pointer 3 here, where, okay, if we're going to change where this is pointing to, maybe we don't need the memory that it was originally pointing to. Let's just go ahead and delete it before we even do that. And this will also give you 0 memory leaks. So I know that got confusing there in the middle. Any questions on this?
Yeah, real quick.
Yeah.
It's probably an easy answer. Just I'm having a brain fart, but why exactly would you want to allocate memory on the heap for a pointer? Like, why would you want to create what circumstance would you want to create a pointer that allocates memory on the heap instead of the stack?
You mean like why would we do this?
Yeah, like why not just create a pointer without allocating the memory to the heap? So like if you just create a normal pointer and you have the memory in the stack, you know what I mean?
Yeah. So we're doing this in the assumption that we just want new dynamic memory that we want to use within the system. So I think the problem is this is so trivial that your question is more geared to like, why logically are we even doing this?
Yeah.
And I think the answer is more of like, if kind of breaking away from this, we want dynamic memory to be able to do something like we did for the linked list, right? Where we're constantly able to make new nodes in the system, or like delete nodes. And then if we think of like the stack and the queue, you know how we had to make an entirely like new array and then copy everything over, and it wasn't even really new as far as dynamic went. It was just like a new stack one. We could basically kind of make a stack and a queue with dynamic memory using something like nodes, where you keep adding stuff. Did that kind of answer your question?
Yeah, and also if I remember properly, we also don't want to, the more we allocate on the stack, the more memory it would consume too, right? Like not in terms of like your RAM, like it would slow down stuff. That's why you also want to allocate stuff on the heap, right?
So if I understand you correctly, I think allocating more stuff on the heap is actually what's going to eat up your RAM. And then the stack, I think there's a predetermined amount that's on your stack. So I think you'll get like a stack overflow before you'll actually get anything like a like running out of RAM. With stack overflow, the most common thing with stack overflow is going to be too many function calls. Most of the time, this has to do with a recursion call that has no end to it. And basically, you're pushing a bunch of functions on the stack, and then it's going to blow your stack, right? Did that kind of answer your question?
Yeah. Thank you.
Perfect. Yeah. Yeah, and those for you guys that came, the thing I showed with the RAM, that was all dynamic, where I had that like loop that basically created a bunch of memory in RAM. Like it was like a for loop that made a bunch of new calls. that that is what like ate up a bunch of my RAM, if you guys remember that. So okay, cool. So that is that on that. And then now we get to the pass by reference and all that good stuff. So let me go ahead and clear the screen because we don't need that drawing anymore. Okay. Cool. So I did this kind of backwards in my other lab. Let's do it differently this time. So we'll go over the pass by value and just remind ourselves why this is going to be an issue. So this is a super common example when dealing with or a super common example when trying to prove pass by value versus pass by reference is swapping. So we have a integer called x here, that's 7, a y integer called 10, and we just want to swap those values and we want to pass that to a function, right? So we want y to be 7 and x to be 10. So most people think the simple swap procedure would be just passing them in and then having a temp variable so we can preserve one of them and then just switching what they are, right, and printing them out. But for those of you who have been kind of paying attention to everything, will know that this won't work. So this is going to be, we're going to end up getting 7 and 10. So x is still 7 and y is still 10, and that's not really what we want, right? So that's basically because we're passing by value. When we pass by value in C++, it is passing a copy to the function call. And to make that super clear, we can actually print out the address of x. And what this will give us is some memory address that's actually going to be different than what it is inside of the actual function. So if we do it this way and print this out, what you guys will end up seeing is that these memory addresses are actually different. So hopefully that kind of drives home that we're manipulating two different objects. When we set this x to y, that's not referring to this x right here. This is, again, considered passing by value. To actually make this work, we need to switch this to pass by reference. That is done by just simply making these a reference. It's going to take in a reference, meaning you just put the ampersand operator. Doing it this way, if we go ahead and copy this and paste this in here, when I go ahead and run this one, and actually should have left that old one up there, but oh well. When I run this one, you can see that these addresses are going to be the same, which is important because that's what we want. We want to pass the actual object itself, not a copy of that object, because the function can manipulate a copy all at once, but as soon as that function pops off the stack, that copy is going to be lost in space. So we need to actually give it the actual object itself, and that's how we get these things to properly swap. The kind of sort of like third option or 2B rather. Yeah, Franco, what's up?
Real quick, just to make sure, if we were to pass an object by value into a function, it would call the destructor once the function's gone, right? Because it falls out of scope. If we would pass it by value.
Yes. Yeah. Yep. Exactly. Yeah. It would pass out of. Yes, that's right. Cool. So the two, like 2A or 2B rather, is to pass by reference, but use pointers instead of references. This syntax ends up being a little bit more like nitty gritty. You got to do more stuff here, but you do need to understand both for sure if you're going to work with C++. So this way we're passing in pointers, which means when we come down here to the parameters, we actually need to pass in the address, right? Because pointers store addresses. So we need these things to be to actually be addresses that are passed in. And when we do this, because these things are addresses, we actually need to dereference all of them, which ends up, again, making the syntax a little bit more ugly. But the functionality here is going to end up being the same. And I didn't print the address of it here. Let's go do that. But yeah, there you go. So the address is different. And what I mess up? Because that's why is that happening? I know why. So why these look different is I'm actually getting the address of the pointer, which isn't the actual object itself, right? The pointer would just be X, and that's actually what's storing the address. So now they're going to be the same. So I wasn't getting X's address. I was getting the address of the pointer that's pointing to X. So, yeah. Okay. So another thing we can kind of think about, because a lot of people kind of understand this, but then kind of some understanding breaks down, I think, when they see other things. So if let's keep swap 1, because I think that's the easier one to deal with. Something that gets people on the exams a lot is just not paying attention to what these parameters are taking in. So they'll kind of look at this and ignore whether it's a reference or not. So like if one of these isn't a reference, like y is just a normal pass by value. Now we're passing x by reference, but not y. So if we were to run this, you're going to see that like x changes to what it's supposed to, but y isn't going to, because we didn't pass y by value. So it's going to just change a copy rather than the actual thing, right? Another thing to keep in mind is the same applies to any other type of like object. So if we had like a vector, that's just like a normal integer vector called x, and let's do x pushback like 0, for instance. And then what we're going to pass into swap is actually going to be a vector, a reference to a vector, right? If I can spell vector correctly. Okay. And then instead of doing like swap stuff here, we're just going to call a bunch of pushback calls. So we can do x.pushback 1. So we'll do that a couple times. 2, 3, 4. And the reason that we need to pass this by reference is because if we actually want these pushbacks to be on the actual object that we're trying to pass in here, we need to pass it by reference. Otherwise, it's going to make a copy of this vector. So let's look at this if we don't pass by reference. We basically do x.pushback 0. It goes into the function called swap. It's not really swapping anymore, but you get the idea. It's trying to do a bunch of pushback calls. And then we're going to iterate over this vector and try to print everything inside this vector. If we do this, as you guys can probably guess, we're only going to see like one print call, right? Vector add 0, because that's the only thing that exists. All of these other pushes weren't actually persistent because we passed a copy of our vector in. To actually make this work, we need to pass a reference to our vector. So it's the actual vector itself. Now, when we do this, these pushbacks will be persistent and will actually push back on our actual object. Questions on that? Cool. So the last thing that I kind of have to, well, let me say one more thing about this. The other thing that we pass like by reference for isn't just to manipulate the correct object, but it's actually for speed, right? And if you think about this, if we pass by value, it's got to make a copy. And think about that vector. If that vector had like thousands of elements in it, and we had to pass that by copy, it has to copy everything in that vector over, and these function calls become incredibly slow. So if we pass by reference, all it's got to do is pass one address, which is going to be usually a 4 byte. What did I say earlier? Like 4 bytes, which is way quicker to pass than a massive vector. Okay. So that's another reason we want it. So the last thing I have to go over here is just going to be some stuff with const, and then I promise I'll be done. I just lied. So the only questions I have for the stack and queue, which you can see the answer here, is basically what's the insert and remove functionality of a stack. It's going to be LIFO. So just remember, a stack has the principle of last in, first out. So the last thing we put on the stack is going to be the first thing that we pick off. Just think of it as a stack of plates. That's the best way to remember it. With a Q, I would say that it's FIFO, so first in, first out, and just think of a line, right? If you're the first person in line at Disney for a ride, you would expect to be the first person on that ride, bar any fast passes, right? So, and if you're in the last person in line, you're going to be waiting a long time to actually get on the ride. So thinking of it those two ways, and then just remembering, okay, LIFO, last in, first out, and then FIFO, first in, first out. Okay, now I promise is the last thing, const. So we'll kind of go over the difference between a const, like int using pointers, and like a const pointer to an int. So with this syntax on 312, if we have int and then const and then star x equals the address of y, where these are just integers. What this means is that like what it's pointing to is constant. So we can change the pointer all we want. We can change where this pointer is pointing to, but what we can't do is change the actual integer that exists at that location, right? So we can't dereference this pointer and then try to change that, because the actual integer at that location is what's const. On 316, right here, what this is, it's a const pointer to an int, meaning the pointer itself is constant, so we can't change where the pointer is pointing to, but we can change the value at that pointer. So if we dereference that pointer, we can change that integer all we want. And then line 320 is kind of a combo of both of them. It's const int star const, and then whatever the name of your pointer is. And this is actually going to protect both the pointer and the integer at that pointer, so you can't change anything about this. And that's kind of what these syntax look like. So not much to say about that other than that's just what the syntax is. So make sure you're familiar with those concepts. So
it's like depending where the asterisk is.
Yeah, I've tried to like make sense of it myself as well. I think, yeah, I guess the best way to think about it is just where like the const is, where like this is an int pointer and then it's const, and this is an int const and then pointer. Like so it's like, yeah, I personally have trouble making sense of it, like just reading it. To be honest,
like, yeah, but if when we're declaring, right,
yeah,
a pointer, we can put the asterisk either after the int or before the const, right?
Yeah, so like you're saying if you did something like this, that's perfectly fine.
But that only works. So that's when we're declaring a constant pointer, right? But if we want the int to be constant, we have to kind of put the asterisk after the constant, right?
Yeah, you could do this. That's fine. Like basically in these three spaces right here, you can put the pointer anywhere you want like that. But you can't put the pointer over on this side. Yeah. Because then it would become a const pointer. Yeah.
So the best way for this stuff is just to kind of like memorize it, right? Because it's hard to make sense.
I think so. There's probably a way to break it down and make it make sense. I'm probably just not thinking about it. Honestly, to me, it almost looks opposite of what it should be, but it might be the way I kind of conceptualize these pointers. But you can see that where I'm getting the error codes, that the comments I have at least are correct, because if this wasn't a const pointer, then it would allow this to happen. And that's what these red squigglies are. It's because it's not going to let me change these things. So, yeah. Cool. So I'm here to help you guys on anything you guys need, questions, labs, anything you guys got going on. So hopefully this was helpful. And if you're heading out here, best of luck on the exam and the lab you guys have this week.
Okay. One more time, just to double check here, so I'm writing the correct stuff down. The
first absolutely.
Int is you can change the memory address of the pointer, but whatever the data, so like the x, you can't change.
Absolutely, correct.
But if we change the memory address of the pointer, it's technically not pointing to x anymore, right? So there's just x somewhere, but you can't change x.
Yes. Yep. Okay, kind of, yeah, because x itself is the pointer, right? So there is, if you change where the pointer is pointing to, really it's more that x was originally pointing to y, and we can't change what y is. right?
Oh yeah, so no,
But
you can't.
yeah, if we move X, like that variable will still be persistent, if that makes sense.
Yes, the
Like
X
we
is a
still, yeah.
So the first one we can't change Y, and then the second one we can change Y, but we can't change the memory address. So we can't. So it's always going to be A will always point to Y's memory address basically.
Yes. Yep. Yep. Exactly.